Welcome to this explainer. Today, we're looking at how one single, frankly, impossible-seeming lab accident back in 1895 completely revolutionized modern medicine. We're talking about a discovery so profound that it suddenly allowed us to see right through solid matter, through wood, through rubber, and, yeah, through human flesh. I mean, try to imagine living in a time before anyone could see what was beneath the skin without using a scalpel. And then, literally overnight, everything changes. To really grasp the impact of this, I want you to put yourself in the shoes of Anna Bertha Röntgen. Her husband, who was a physicist, calls her into his pitch-black lab and asks her to just place her hand in front of this strange, glowing tube. And when she does, she doesn't get a normal picture of her hand, she sees her own skeleton. Her wedding ring is just seemingly floating around this bare, ghostly bone. It was an absolutely terrifying yet thrilling moment in human history. Her reaction? She reportedly shuddered and said, "I have seen my death."
So what exactly was going on here? How did a completely sealed, blacked-out cathode tube cause a chemical screen to just start glowing on the complete opposite side of a dark room? I mean, the tube was wrapped in thick black cardboard. Absolutely no visible light could get out, yet something invisible was shooting across the room, passing right through the cardboard and hitting a screen coated with a chemical called barium platinocyanide. It absolutely shouldn't have been happening, but, well, there it was.
Section 1. The accidental discovery. The guy at the center of this impossible phenomenon was Wilhelm Conrad Röntgen. He was a physics professor at the University of Würzburg in Germany. And if you look at this incredibly rapid, almost obsessive timeline of his work, you can really see how consumed he was by this anomaly. In November 1895, he notices that faint glow, but instead of just writing it off as some weird fluke, he basically moves into his lab for weeks. He tests everything. Can this ray pass through paper? Yes. A thick book? Yeah. A wooden board? Yes. Aluminum? Mostly. And then comes that famous hand shadow experiment, where he tested it on his wife, creating the very first human X-ray. By December 1895, just weeks after spotting the glow, he publishes his findings to the entire world. Now, because he was a man of science dealing with something completely inexplicable, he named it after the mathematical symbol for the unknown, X. He genuinely had no idea what these rays were, only what they could do. And here's a detail that tells you exactly the kind of person Röntgen was. In 1901, he was awarded the very first Nobel Prize in physics for this, but he completely refused to patent the technology. He believed that a discovery this monumental should belong to all of humanity, not just him.
Section 2. Inside the atom. To see how this transitions from a historical mystery into hard science, we really need to look at exactly what these rays are. And this perfectly explains why X-rays behave the way they do. See, X-rays are part of the electromagnetic radiation family, right alongside visible light, radio waves, and microwaves. The big difference is the wavelength and the energy. Visible light has a wavelength of a few hundred nanometers, but X-rays? They're unbelievably tiny, roughly the size of a single atom, somewhere between 0.01 and 10 nanometers. And because that wavelength is so incredibly short, they pack a massive amount of energy compared to normal light. That high energy is the exact reason they can just punch right through materials that stop ordinary light dead in its tracks.
So how do we actually make them on demand? Well, inside a modern X-ray tube, there's a cathode, which is basically a heated filament, kind of like what you'd find in an old-school light bulb. That heated cathode releases a stream of electrons. Then you apply a massive electric voltage. We're talking over 100,000 volts. This huge voltage acts like a catapult, slamming those electrons into a tungsten target called the anode at a significant fraction of the speed of light. When those electrons crash into it, they rapidly decelerate. All that energy has to go somewhere, right? So it gets released as X-ray photons.
Actually, there's a fantastic term for this specific physical reaction, Bremsstrahlung. It's German for breaking radiation. When that incoming super-fast electron gets close to the strong electric field of a tungsten nucleus, it gets sharply deflected and is forced to slow down, or break. And whenever a charged particle decelerates like that, it spits out energy in the form of a photon. This specific braking action is actually the most common process for generating the X-rays your doctor or your dentist uses on you today. But get this, here's a truly wild statistic about that whole process. Out of all that incredible energy generated by those electrons slamming into the tungsten, only 1% actually becomes X-rays. Just 1%. The other 99% simply turns into a massive amount of heat. That's why, if you ever take a close look at modern clinical X-ray cubes, they are heavily engineered with serious, heavy-duty cooling systems, because without them,
The machine would literally melt itself.
Section 3. Casting shadows.
Okay, so now that we have this beam of high-energy photons shooting out of a tube, how does that actually translate into an image of your ribs or your lungs? It all boils down to a concept called differential absorption. Basically, different materials in your body absorb X-rays at completely different rates depending on their density and their atomic makeup. Bone, for instance, is packed with dense calcium, which is a relatively heavy element, so it absorbs and blocks a lot of the X-rays. On the flip side, soft tissues like muscle, fat, and your organs are made of lighter elements like carbon and oxygen. They let a lot more of those rays pass right through. And the air in your lungs, it barely absorbs anything, letting almost all the rays pass right on by.
So, the absolutely crucial thing to remember here is this. An X-ray image is not a photograph of your body. It is literally a shadow map showing how much radiation was absorbed on its way through you. Wherever the X-rays pass right through your body and hit the detector on the other side, that area turns dark. But wherever the X-rays get blocked, like say by the dense calcium in your bones, the detector on the far side stays light or white. Those white bones you're looking at on the doctor's screen, they aren't glowing, they are literally just shadows cast by radiation instead of visible light.
And what's really amazing is that this same 1895 physics is still the foundation of our most advanced diagnostics today. Take a modern CT scan, for example. It uses this exact same principle of differential absorption. It just takes hundreds of X-ray images from all different angles as a machine rotates around you. Then, it uses a computer to reconstruct all those 2D shadow maps into a full, navigable 3D model of your insides. It's the same exact core concept, just multiplied.
Section 4. The hidden dangers.
Now, of course, a tool this powerful didn't come without a catch. For decades, humanity treated this immense invisible power with just shocking carelessness, mostly because nobody understood the real risks of ionizing radiation yet. In the early 1900s, X-ray machines were practically treated like carnival attractions. I mean, you could literally go to a shoe store and blast your feet with radiation just to see if your new shoes fit right. They were used at fairs for cheap thrills, and they were even aggressively marketed to women as this high-tech way to remove unwanted hair. And because of this completely reckless application, many early scientists, technicians, and everyday people suffered severe burns, radiation sickness, and fatal cancers.
Those early tragedies were a very, very hard lesson, but they're exactly why X-rays are so tightly regulated today. There is absolutely no need to panic when your dentist brings out the machine. A single modern chest X-ray delivers a tiny, carefully controlled dose of radiation. Just to put into perspective for you, it's roughly equivalent to just a few days of the natural background radiation you absorb naturally just by living on planet Earth. The heavy lead aprons, the shielded rooms, the strict dose limits we have today, all of that exists because we had to learn the hard way to respect the immense power of Röntgen's unknown rays.
Section 5. Accident to modern medicine.
So what started as a strange, unexplainable glow on a chemical-coated screen in a dark German lab eventually evolved into one of the most defining, life-saving tools in modern medicine. And it happened almost entirely by accident. Röntgen wasn't originally looking for a way to see inside the human body. He was literally just trying to understand a weird anomaly. But he succeeded because he had the deep scientific curiosity to actually chase down that mysterious glow instead of just shrugging it off. It just goes to show you the biggest discoveries really do come from paying attention to the thing that shouldn't be happening.
Which leaves us with a pretty fascinating thought to end on today. When we look at the highly optimized, hyper-focused world of modern science, you really have to wonder, what other world-changing discoveries are hiding right now in the little lab accidents and data anomalies that we just ignore every day? Keep paying attention to the unknowns, because they just might change the world. Thanks for joining me on this explainer, and I'll catch you in the next one.